Okay, so we were talking about jet schemes. So I introduced, well, I still haven't really defined jet schemes, but I started with somewhat abstract discussion, which was meant to put jet schemes in the context of SLT, at least at a high level. And the idea is that we're trying to understand the geometry of the vanishing set of some KL divergence. That's an analytic function. Maybe we can find an equivalent polynomial. And the geometry of that vanishing set of that polynomial relates to learning behavior in ways we're trying to understand. One of those ways is to try and understand what information is in the resolution. And then there's some conjectures of Nash and results, sort of a whole story there, but at some level, some of the information we care about in the resolution, which the theorems in Watanabe's book and elsewhere tell us that that structure relates to, say, generalization error. And some of that structure can be seen also in what's called the arc scheme. So the arc scheme is a limit of the jet schemes xn for all n. Okay, so that's a very high level reason to care about jet schemes. What I want to try and do over the remaining lectures in this series is to try to steadily pin that down into something that is more like learning behavior in some sense you might recognize. For example, the dynamical system of a network being trained, or rather, perhaps more realistically, sampling from the Bayesian posterior as a process. So, okay, that's the aim. Yeah, this was kind of some sort of abstract categorical way of realizing what the jets to a scheme are. It's not important really if this went over your head, but the point here was to get to, in some abstract way, justifying that we care about K-algebra homomorphisms like this. This is an n-jet. So I'm still going to continue with this as a sort of abstract definition. I then unpack that a little bit in the case of one jets and two jets, or rather just one jets. Maybe not here, maybe I think the next set of boards explain this. Right, so I think I finished on this calculation, yes. So what I was doing in this pair of boards was to explain how a K-algebra get the right board open. So sim v star, V is our space. Sim v star is polynomial functions on the space. That's a K-algebra. K is our field. It's always going to be an algebraically closed field for simplicity. Well, I guess since we're talking about real functions, I shouldn't say that perhaps. Yeah, I take that back. So K is any field. We're looking at K-algebra homomorphisms from sim v star to A. A is this quotient ring, kt mod t squared, which just means linear combinations of 1 and t with the relation that t squared is 0. Okay, so that's the algebra, and then I was computing for you or classifying K-algebra homomorphisms from sim v star to A. And the way I did that was to look at the Taylor series expansion of f. So f is a function, a polynomial function on V, viewed as an element of sim v star. I can take the Taylor series expansion, and if I apply to it some K-algebra homomorphism psi, and I've written here psi sub pq, now that's because given any psi, I can evaluate psi pq. So given, how should I say this? Given any psi from sim v star to A, by the universal property of sim v star, which I also discussed last time, such a K-algebra homomorphism is determined by what it does to the generators, and those are the xi's. Those are the coordinate functions on V. Okay, so evaluate psi on xi. That's an element of A. An element of A is a linear combination of 1 and t. Call the coefficients pi and qi. So those are scalars. Okay, so any psi determines these two sequences of scalars, pi and qi. And I'll collect them together and call them p and q. Okay, so that data, p and q, is determined by psi and determines psi by the universal property. So I'll just write psi pq for the psi that sends xi to pi plus qit for all I. Okay, so if I fix a psi and I evaluate it on an f, what I get is what we computed here. Now I think we must have run out of time because that's kind of an awkward place to stop. So maybe I'll finish that thought and then continue on. So the point of doing that calculation is to convince you that it's reasonable to think of psi's as tangent vectors. Right, so the upshot is that, well, first of all, every K-algebra homomorphism from sim v star to kt mod t squared is of the form for some p and q in V, unique p and q. Okay, so that's what K-algebra morphisms between those two rings look like. They're in bijection with p's and q's, pairs. So there's a bijection which I wrote earlier. And you could say the map is this way in the sense that given PQ, this formula defines a K-algebra homomorphism, and that map is a bijection. Okay, so I've proven that. I've proven there's this bijection. Okay, now I need to convince you that it's reasonable to think about this data as a tangent vector, and the formula hopefully makes that clear, right? So psi, what is a tangent vector? Well, there's many ways of defining tangent vectors. But usually you would say a tangent vector is a function assigning to a germ of a function at a point a scalar. Maybe that's not the way you think about tangent vectors. Maybe you think about tangent vectors as equivalence classes of curves through a point. That's fine. But this is an equivalent point of view. So this is the point of view which says that a tangent vector is a derivation of functions. And we see here the latter point of view. So psi sends a function f to, well, its value, a pair consisting of its value at a point. That's not a derivation, but this part here is a derivation. Right? Sending f to this expression is the tangent vector q. Right? So under the normal prescription, if you were to assign to q a tangent vector at p, it would be exactly the function which assigns to f this second term I underlined. Okay, so basically by definition of a tangent vector, this data, this psi, is a tangent vector together with this extra information, the evaluation at p. which says where it is a tangent vector. Okay, so this is the argument that 1 jets to V equal tangent vectors. To V. V is just affine space. And the left-hand side was defined to be these K-algebra homomorphisms, right? So I've now given a geometric interpretation of these K-algebra homomorphisms. Any questions? So this is kind of wrapping up last lecture, I guess.
Can you remind me what a germ is, sorry?
Germ, yeah. So germ just means an equivalence class of functions where the equivalence relation is that they agree on a neighborhood of a point. So if I have a point P, U, V, so a germ, you would take a pair U and a function F, which is defined on U, and it would be equivalent to the pair VG if and only if there exists an open set W contained in U intersect V and containing P with F restricted to W equals G restricted to W. So the equivalence classes of that relation are called germs, and if you take the set of all germs, that's a ring, and derivations of that ring, so assignments of scalars to elements of that ring of germs which satisfy the Leibniz rule with respect to multiplication. That's one definition of what a tangent vector is. If you take the functions f and g, if you take them to be smooth functions, so germs of smooth functions, then you get the usual definition of a tangent vector in differential geometry.
Cool, thanks.
Yeah. Okay. Well, that's fine. We've talked about 1 jets, but only to affine space, which is a bit boring. So now I want to talk let me see. So yeah, I'm going to say something about jets to more interesting varieties. Ultimately, we're interested in vanishing sets of functions like k and h back on the first board, right? So jets to algebraic varieties. Okay, I'm just going to stick with one equation, but everything I'm going to say generalizes to multiple equations. So we're going to suppose we have a function on our space V. I'm just going to identify this with the polynomial ring in the xi's. I recall that the notation I introduced earlier is that V has a basis E1 through En, and xi is the dual basis. And z is going to be the vanishing locus of f. So think about, there's V, and here's Z. There's maybe a P, and maybe there's the gradient. Okay, so what's an n-jet or an m-jet to Z? So an m-jet to Z as compared to V, right? I've already defined what an m-jet to V is. It's a k-algebra homomorphism from sim V star to kt mod t to the m plus 1. So an m-jet to Z, a subvariety, is by definition a k-algebra morphism from the ring of functions, ring of polynomial functions on Z, which is the quotient of sim v star by the ideal generated by f. Now I'm just presenting these as definitions. The motivation for this definition comes from unpacking the content in this. I'm handing you this definition, and then we'll unpack it and see what its geometric content is. But yeah, this in some sense no motivation beyond just observing that it has some information that is geometrically relevant. One can give more of a motivation, but we won't do that here. Okay, and the mth jet scheme of Z is the space of all m jets. Again, this is not the place to introduce schemes. I just want to have that idea in your head that this is what an m-jet is, and if you took the set of all m-jets, that set has more structure. It's a topological space. It has a notion of regular functions on it. It defines what's called a scheme. And we'll compute an example. So I'll compute the two-jet scheme of a singular curve, hopefully at the end of today's talk. And it will just be defined by some equations, and you won't need to know what a scheme is. Okay, so let's give some examples. So let me take m equals 0. So if m equals 0, and a zero jet to z is just a k-algebra homomorphism from this quotient to kt modulo t to the 1, which is just k. So what is a k-algebra homomorphism from this quotient ring to k? Well, that's determined by where I send the variables, right? So let pi be defined to be the image of the variable xi in that quotient ring. Well, for psi to be well defined, it has to send f to 0. What does psi do to f if it sends all the variables to pi? Well, it just sends, if you think about it, it's just looking inside f and replacing each xi by pi, which is what it means to evaluate f at p. Okay, so we see here that 0 jets to z, which are these psi's, are exactly the data of, so if p means the point with these coordinates, 0 jets to z, that is psi's, if you extract the data of the pi, that is the image of the variables, it's exactly the data of a point where f is 0, but that's the same as a point of z. Okay, so 0 jets to z are the same as points of z. And the mth jet scheme I'll denote by Zm. Or, I take it back. I'm not sure what notation I was using earlier. Maybe it was Zm, but I'm going to write Jmz. The mth jet scheme of z. Okay, so this means that J0 of z is just z. Or rather, it's canonically isomorphic to z. What about if m is 1? Well, that's what we just discussed. So then psi is a k-algebra homomorphism from this quotient to kt modulo t squared. If I take pi plus qit and set it equal to psi of xi, as we just discussed, then the equation 0 equals the image under psi of f is exactly, looking at the previous board, the first equation. That means that fp plus the gradient of f dot qt is 0, But this is in kt modulo t squared, in which 1 and t are linearly independent. So that says two equations. It says 0 is equal to fp, and it says that 0 is equal to the gradient of f at p dot q. Well, this just says that p is in z, and this says that q is in the tangent space to z at p, right? Because the things that are orthogonal to the gradient are exactly the things that are tangents. All right. So these two equations say that PQ are in the tangent space, or the tangent bundle to Z. The tangent bundle to Z is a space where the points are pairs consisting of a point in Z and a tangent vector at that point. So Q. Okay, so what this says is that J1, which is the space of all 1 jets, is the tangent bundle to Z. 1 jets to Z are tangent vectors to Z. Alright, so this is meant to convince you that at least for m equals 0 and m equals 1, the notion of an m jet to an algebraic subvariety has a clear geometric content. It just gives you points, respectively, and tangent vectors. Once we get to 2 jets and beyond, they're less familiar objects. All right, any questions?
Is it fair to say that if we are only concerned about local property near a point, we can always restrict calculation to similar to what you have done here, which is like, as in we don't need to care about the global scheme structure, we just need to care about affine patches. Yeah,
that's right. Yeah. As in most of algebraic geometry, things can be done locally. So the jet scheme is a local construction. So if you want to do the mth jet scheme of Z is locally pieced together from the jet schemes of open subsets of Z, which you can assume to be affine. So I'm presenting here the affine story, but in some sense that is the whole story. That's right. And then there's how it fits together.
What is missing though?
Sorry?
Sorry, yeah. So, what is missing from this local story? So what kind of information could be missing?
Well, it's a bit similar to the blow-up.
I know it's like topological, right?
Well, in some sense, nothing is missing. The jet scheme is those local pieces together with how they glue together. But the information of how they glue together, of course, is real information. So it's not that you know everything by just knowing the affine opens.
Right. Okay. Yeah, I'll ponder that. Thank you.
Cool. All right. So I want to talk about 2 jets. Let me see. Yeah, maybe it's... So rather, I want to talk about 2 jets to algebraic subvarieties, which, first of all, I just want to recapitulate that calculation with the Taylor series, but keeping more terms so that we understand what 2 jets are. And I think that's best done on the next set of boards, so we'll just move over. Oh. Whoops. Okay. I forgot that we had Matt's talk here last time, so yeah, we should proceed further. Okay. So 2 jets. So note the canonical surjective K-algebra morphisms from kt modulo t cubed to kt modulo t squared to k. And these just send t to t to t. Yeah, I think I'll call these pi 2, 3 and pi 1, 2. Yeah, I guess the swimming is a bit distracting. That's the fault of the location. Sorry, yeah, thanks. Okay, so the point...
Dan, what do you mean?
Sorry?
What do you mean by sending t to t and k in the last map?
Yeah.
Right.
A good question, though. Yeah, there's no t there. Yeah, thanks. Okay, so these K-algebra morphisms mean that we have natural maps from 3 jets, or rather 2 jets to 1 jets to 0 jets, right? Because, well, remember that a 2-jet is a K-algebra homomorphism from something into this guy. So then I can compose with this and get a K-algebra homomorphism into this guy, which is a 1-jet. So 2 jets determine 1 jets, 1 jets determine 0 jets. And we've already seen this in action. So while I'm writing, think about how you would extract a point from a 2-jet, sorry, from a 1-jet. And so I just said that 1-jets are tangent vectors, but sort of based tangent vectors, right? They're sort of a tangent vector that knows where it is. So if you take where it is, that's a map from tangent vectors to points. And that's exactly what this map here does. So if you take psi pq, it just extracts, well, the evaluation at p, right? That's the map that sends a function to its value at p, and that's the function, the K-algebra homomorphism that corresponds to the point p. Maybe that's mixing metaphors a little bit. So it's either, you can think about it as the K-algebra homomorphism that sends psi pq to evaluation at p, or you can think of it on the other side of the bijection as pq goes to p. Okay, so m jets determine n jets for every n less than or equal to m. Well, so what that means is that in understanding 2 jets, I just have to understand the extra information, right? So a 2 jet is in particular the information of a 1 jet and some extra stuff. So I don't need to interpret sort of 2/3 of the data. Okay, so let's see. Let psi, I'll start with a 2-jet just to affine space, and then I'll introduce the equation. But let's just suppose we're given a k-algebra homomorphism psi. What's the data in there? Well, again, we just evaluate it on generators, but now we get 3 scalars per generator. Right, so we're going to set pi plus qit plus rit squared to be the image of the ith generator, right? 1 tt squared are a k basis of kt mod t cubed. All right, so that's the data that determines psi. And that's basically all there is to say about it, right? By the universal property, to tell you a psi is exactly to tell you these 3 scalars for every I. So that's it. That's a bijection of psi's, k-algebra homomorphisms, or 2 jets to affine space with triples. Right, so if I let P be that point, and Q similarly, and R as well, that's a bijection by the universal property of the symmetric algebra. Okay, but we still want to know what this psi corresponding to PQR actually does. Right? So if you give me a psi and it has PQ and R as its data, what does it do to an F? So that's the calculation I want to now do. So given a psi as above and an F in sim v star, well, again, let me just take the Taylor series expansion of F. But now the calculation will be a little more interesting, because before I applied psi and then threw away terms of order 2 and higher, right? Because t squared was 0 in the codomain of psi. But now psi is a 2-jet. So in the codomain of psi, t squared is non-zero. So I will keep more terms. Times all this stuff. Okay, so apply, so that's an equation that holds in sim v star. Now apply psi to it, which is a k-algebra homomorphism. So that's a scalar, remember, right? I evaluated that partial derivative of f at p. These are actual polynomials, so we'll get psi of that, but that's psi of this times psi of etc., and the powers can go outside the psi as well. So I'll skip all that intermediate stuff and just get straight to psi of f is, I'm just going to write I underline for these indices here, and I'll write I underline factorial for that. Maybe I won't be that lazy. Okay, so I get psi of x1 minus p1 to the I1 dot 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 psi of xn minus pn to the in. Okay. So what is psi of xi minus pi? Well, that's psi of xi minus pi. Psi of xi is pi plus qit plus rit squared, right? So that is qit plus rit squared. which is t qi plus rit. So psi of f is sum over I, 1 over I underline factorial so each of these is going to get replaced by that for a suitable I. So I'll get t to the power of all those i's, and that's I1 plus I2 through In, so I'll get t to the modulus of I, meaning I1 plus dot 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 In, and then I'll get Qi, well, it'll be the product from I equals 1 to N, Qi plus Rit, or J rather, to the Ij. Now, remember all of this is modulo t cubed. So any terms of order 3 and above I don't need to worry about. Okay, so let's think about how we get quadratic, linear, quadratic, and cubic terms out of this expression. Let's start with order 0 terms. Yeah, can you see what the order 0 term? Maybe I've made a mistake here. Yeah, I guess we don't actually need to do the calculation for the 0th order term and 1st order term, although maybe I'll sketch how you can see them, just to point out why we only need to compute the order 2 term. That was kind of the point of drawing this diagram at the top of this first board here, right? So if I take psi, which lands in kt modulo t cubed, and I'm post-compose with the map to kt modulo t squared, so that takes alpha plus beta t plus gamma t squared and just sends t to t, but now t squared is 0, so that's alpha plus beta t, right? So I know what the first 2 terms here are, because so they must be f of p and the gradient of f at p dot qt plus something. Right, I just don't know what the something is, but I know that the first 2 terms must be this. Hello? Is that you, Ben? I can't hear you.
No, I can hear it too there.
Oh, okay. Was somebody asking a question? I couldn't hear you. All right. Okay, so I hope that's clear. So I mean, we can see it from the formula. It's just no reason to go into it. So if I want to get the 0th order term, then I need I underlined to be the 0 vector, which means I'm not taking any derivatives. And then here I also get 0 powers, so I just get f evaluated at p, which is the 0th derivative of f evaluated at p. If I take the first derivative, then you can see you get to choose exactly one of these indices to have the value 1 and the other 0, and so you get the first derivative, and the dot product comes from this part here. But I'll focus on the 2nd order term, since that's the new information. Okay, so let's say t squared stuff plus lower order terms. Can you turn it down, please, a little, Russell?
Yeah.
And if you're finished, mate, can you go back in the other room? You finished your food? Okay, so let's see which terms will actually contribute. Just trying to understand my notes here. So there's two places we can get t's from, right? We can get them from t to the power of the modulus of I, or we can get them from those brackets. So maybe the thing to do is to worry about when we get okay. Let's think about it that way. So here's our two sources of t's in this formula, right? Let me call them source 1 and source 2. Now, if we're going to get a t squared, then either we get 0 powers of t from source 1 and 2 from source 2, or we get 1 from each, or we get 2 from source 1 and 0 from source 2. Right? There are no other possibilities. So let's think about what it would look like to get 1 from... just think about which way I want to write the terms. Okay, why is this obvious? So we can throw away cubic terms, right? So we're working modulo t cubed. So we can throw away any terms that, so we should think about the index I guess, right? So this index I here, we only care about indices that are, well, we get contributions if that's equal to 2, right? Because we can take the q's here and multiply them with t's here, but only sums that have indices with 2 or less contribute. So what tuples of non-negative integers can you make that add up to less than or equal to 2? Well, you could have 0, all zeros, or you could have a 1 somewhere that will add up to 1, and that's the only way to have them add up to 1. Yeah, I just don't think that this factoring out the t has really helped, has it? Okay, so the this term here came from, this was having a single I1 non-zero, right? Okay, so when I is all zeros, it just contributes the FP term, and there's no other bits contributing. The tuples I underline where one entry is non-zero and is a 1, that is the sum, the tuples where the modulus is 1, those are the things that contribute something like this first line here, right? Because t times qj plus rjt is exactly psi of xj minus pj. All right, so these here are exactly the cases where this is equal to 1, The next line, these two together are the cases where I is equal to 2. Right, it's just whether or not I have I equal to j or I different to j, and then you can pay attention to the factorial and see that the coefficients are correct, so I'm not double counting or whatever. Okay, so these are the terms I need to pay attention to, and then I get to throw away terms that are cubic in t. So for example, if I expand out that product of t squared with t and t, it's going to be 0, or if I take that product, it's going to be 0, etc. So I'll just perform that throwing away, and I'm left with t squared. Okay, so let me take the product I get from multiplying this t with this factor here. The other factor, where I multiply the t with a qj, that's the dot product term on the left-hand board at the bottom, the gradient of f at p with q. Right? So I've already accounted for that. I'm just getting the t squared terms. So what I get here is the sum j equals 1 to n of rj at p. That's the term we just talked about. What's going on with my pencil? Okay. So the next term, need a moment to fix my pen. The next term comes from the next line. How do I get a t squared? Well, I have to choose qi and qj when I expand the brackets, right? So that's sum I less than j qi qj, and then in the third line I have to choose qi. Plus lower order terms in t. Okay, so to conclude, this is t squared r dot gradient of f at p plus, and this is an interesting sum, and the whole point of doing this calculation is to discover this expression here. Sum over ij, qi, qj times the second derivatives of f. All right. Any questions about this calculation? Now I'm going to interpret it, but this was the hard part. Okay, so definition. Given a symmetric matrix H, we're going to define a bilinear form by saying take two vectors, pair it according to H by just doing this, which is of course sum over ij, qi, hij, qj. Roblox just crashed on me. Okay, so this is a standard way of producing a bilinear form from a symmetric matrix. It doesn't have to be a symmetric matrix to write down this formula, of course, but if we want a symmetric form, it needs to be a symmetric matrix. So the second term in that bracket is the pairing of Q with itself according to this pairing where H is the Hessian. So definition. The matrix of second order derivatives of f at P is the Hessian of f at P. So we've now proven. So you can interpret that matrix as a pairing, a bilinear form, on the tangent space at P. Q are tangent vectors. So the lemma we've proven by the calculation on the previous board is that there's a bijection between triples P, Q, R and two jets. The reason to perform this calculation is that now we can say what the geometric content of a two-jet is, because we can evaluate it at F and see what it means for it to vanish, and that tells us what two jets at a subvariety are. So what we've done so far is we've proven that there's a bijection between triples and two jets, T cubed, where psi PQR of an F is, as I said, the beginning we just have the one jet part. And then the new information is this part. Okay, it's not meant to be clear what this term in brackets means. There's some R, it's a dot product with a gradient, and then there's this term which is the pairing of Q with itself with respect to the Hessian at P. Okay, so that's a two-jet. This formula tells you what two jets are, up to understanding what the term in the brackets means. So next I want to define, just write down for you the equations that would determine the space of two jets of a variety given by the vanishing of a single polynomial, and then I want to compute what all this means for a nodal curve. But are there any questions about the last few boards? Has anyone seen this pairing before? Okay. All right. So let's do the example. We think about where to do it. Yeah, here I'll do. So I'm going to do the same curve we discussed in the context of blowing up. So the example is f is y squared minus x squared x plus 1. The gradient of f is this. V is just two-dimensional. I'm going to write x for x1 and y for x2. Well, so the This is what J0 looks like. That is the curve itself. Okay, so what about the space of 1-jets? Well, remember 1-jets were the same as tangent vectors, that is pairs, P and Q, where Fp is 0, that is P is on the curve, and Q dot with the gradient of F at P is 0. So let's write out what that means in equations. So P and Q are just both pairs of scalars, right? So Fp equals 0 means P satisfies the equation of F, thought about as an equation in P1 and P2. So we'll say P2 squared minus P1 squared P1 plus 1 is equal to 0. That dot product there means Q1 times minus 3 P1 squared minus 2P1 plus Q2 2P2 is equal to 0. And that's it. So the jet scheme is cut out of, if K was R, I guess I wrote it as R, might as well stick with that. So this is in R to the 4 with coordinates P1, P2, Q1, and Q2. So I've just told you a pair of equations which cut out the first jet scheme as a subvariety of R4. Okay, so that's it. That's all the jet scheme is. It's just this pair of equations. All right, well, let's think about what the geometry of this pair of equations are. And the easiest way to understand it is to think about it in terms of its map to J0. Maybe I'll draw it on the next board. Okay, so here's J1, here's J0. So that's J0, the thing I just drew. So let's think about J1, and there's this map here, right? Which is just PQ goes to P. But in J1, we shouldn't sort of be prejudiced about what's more important, P or Q. They come together, right? So just think about J1, Z as being something cut out of R4 by some equations. And we can interpret that, if we like, as pairs of pairs. We call the first pair P and the second pair Q. But J1 somehow exists on its own before that interpretation. Okay, so what does it look like? Well, let's think about it over there's different kinds of points, right? So we need to divide into the case where the gradient is 0 and the gradient is non-zero. Well, that's here, right? The only place where the gradient is 0 and Fp is 0. Right, so where is the gradient 0? Well, if you do the calculation, you'll see that, well, it's at y equals 0 and where either x is equal to 0. Well, I guess we can just do it. So where is the gradient 0? Well, it's y 0 and x minus 3x minus 2 is equal to 0. So that means either x is 0 or x is equal to minus 2/3. But minus 2/3 0 is not on the curve. Right? So that means that the only point where both the gradient is 0 and f is 0 is at the origin. And everything else fits into this category over here. All right, so what does that mean? Remembering that this equation here says q dot gradient is 0. So let's pick a point here and think about what the pre-image is. Let me call this pi. What is pi? Call that p regular. What is that? Well, that's the set of all pairs, PQ, in the jet scheme, such that the first point is P reg, right? Now the way I drew it, the gradient at P reg is non-zero. So this is all the points of the form P reg Q, where Q dot some non-zero vector is equal to 0. How many of those are there? Well, that's a linear equation in Q, right? So that's just the vanishing of a linear form on the Q's. So it's got one less dimension than the space of Q's, which is two-dimensional. So that's just a line. Right? So this here is just a one-dimensional vector space. Okay, so there's a line's worth of stuff sitting over that regular point. And that's true for all the points of the curve, apart from the origin, which is somehow special. Should have drawn this in a different color. Okay, is that clear? So there's over every point downstairs a line, and the blue stuff taken together makes up the pre-image of pi at every point apart from the origin, but the origin is special. So if I take the origin and take pi inverse of 0, well, that's all the points that look like 0, comma q. What's the equation on q? Well, q dot product with 0 is 0, but that's no equation. So that's just all q's. Okay, so that's two-dimensional. It's isomorphic to V itself. So up here at the origin, I have something two-dimensional. Okay, so the way we say it is that we have one-dimensional fibers, fibers meaning these pre-images, away from the origin, but at the origin we have a two-dimensional fiber. So that's what J1Z looks like. If you fiber it over J0, you get this, well, it's a vector bundle. Every fiber is a vector space, but the dimension is not constant. Okay, so I'm going to go further and do the second jet scheme, and that's where I'll finish for today. But any questions about this map first?
Wait, Dan, don't vector bundles have to have the same dimension?
Yeah, I mean, I guess I mean... So it's relative spec of a sheaf, but it's not a locally free sheaf. So yeah, I guess I'm misspeaking. I shouldn't say vector bundle. That's right.
I mean, away from the origin it is.
Yeah, that's right.
That's good enough, right? Yeah.
Yeah, so maybe it's worth, in connection with that comment, noticing that if you took away the origin, so if we take J1Z, remove the pre-image of the origin, and we take this, remove the origin, so that maps to that. Well, that's actually a trivial vector bundle. So that's just the base space, so J0Z, remove the origin, cross R. Right, those are just all the blue lines. Now the reason for that is that and that's a general fact, is that if you take the regular part of Z and take its, so this is actually isomorphic to the jet scheme of the regular part. Oh, sorry. The jet scheme of a regular variety is just trivial. You'll just get something like this. You'll just get the original thing crossed with something. So that's why the jet scheme of something that doesn't have singularities is not interesting. Okay, so let me sort of stack on top of J1 now, J2. Maybe I'll call this rho. So remember, rho sends PQR to PQ. Now, why are we doing J2? Well, we don't quite understand that. I guess I haven't actually properly explained what J2 is, have I? So maybe let's do that quickly. So if I go back to this formula, where is it? Here. Right, so the formula in the lemma, psi PQR, yeah, maybe I should write. So hence, two jets of Z, which is the vanishing locus of F, are in bijection with well, remember that two jets of Z are the same thing as K-algebra by definition. K-algebra homomorphisms from sim V star modulo F to KT modulo T cubed. But that's a K-algebra homomorphism from sim V star to KT modulo T cubed that sends F to 0. And K-algebra homomorphisms from sim V star to KT modulo T cubed are of the form PQR. So sending F to 0 simply means that the stuff on the right-hand side here is 0. So then we get three equations, right? We get FP is 0, which simply says that P is in Z. We get, as before, the dot product is 0, which says Q is a tangent vector. But now we get this final equation, which is quadratic in Q. And this is the equation that we don't quite understand yet. Right? So this here is J2. Right? P triples PQR subject to those equations. Those are the equations of the second jet scheme of Z, which I'll now go back and compute in the case of this nodal curve. Right, so where were we? Okay, so here's J2. All right, so again, we're going to think about different. It's easier to think about the fibers than to think about the thing directly. So let's draw. This is J1. So there's a bunch of lines. So J1 is kind of a union of all the blue stuff. Here there's a plane and more lines. Okay. Let me pick a point here. So that's a PQ. Right, so this is the P. I'm sort of visualizing J0 sitting inside J1 via the 0 section here. But the point in J1Z is this PQ. So a point on this blue line. So Q is sort of the direction that goes along this line. what is rho inverse of PQ? Well, it's all the PQRs. Well, such that P and Q are the given P and Q, and R satisfies that equation I wrote down, right? So R dot product this is minus a half QQ times the Hessian of the Hessian with respect to the Hessian. Now the point I chose is a point where the gradient is non-zero, right? So again, the right-hand side is something, it's some real number, it could be 0, I don't care, but the gradient is non-zero, so I've got an equation that looks like R dot product with some fixed thing is equal to some fixed number. Now that's not linear in R, but I can find a solution, so let R0, for example, just take some multiple of the gradient itself. So find some solution. Then any other solution, if you take the difference with R0, has a 0 dot product with the gradient, and that's a linear equation. So its set of solutions has dimension 1 less than the space of R's. The R's have dimension 2, so that has a one-dimensional space of solutions. So what I get is that this fiber here looks like my R0 plus some one-dimensional space, which if you think about it is in bijection to the tangent space at Z. Okay, so that's a one-dimensional kind of affine space, if you like, but I can give it a vector space structure. So that's another line that lies over that point. Right? So there's a whole line worth of stuff lying over that point, and that's an arbitrary point. Maybe I should draw it in a different color, red. Okay, so every point PQ has a line worth of PQRs over it. So it'd be like there's a two-dimensional space of stuff lying over P in J2. Okay, that's not that interesting. What's interesting is what's happening above the origin. All right, so now let's compute that. Let's take a point. Let's take a point here, which is 0Q for some Q, and compute what the preimage of that is. Well, it's all the things of the form 0 Q R Now the equation is the same, R dot product with the gradient, but the gradient is 0 at P, because P is 0. So the equation is just Q paired with itself gives 0. So the R doesn't do anything. All right? So what I get is that this is, well, it depends on whether that equation is true or not, right? So if it's true, then I get as many R's as there are possible to take, which is a two-dimensional space, just V, right? So I get V if that's true. And I get the empty set otherwise. All right. Okay, so what is the set of Q's for which that pairing is equal to 0? Well, let's compute the Hessian. So the Hessian, so remember our F, maybe let's go back, compute the Hessian back over here. So the Hessian will be, this is at 0, right? I don't care about it anywhere else. It doesn't matter anywhere else. So at 0, I take in the top left, I have the second x derivative, which gives me minus 3. So that's minus 3, sorry, minus, this is the hard part, right? Multiplying integers. Minus 6x minus 2 at x equals 0. These are both 0. And here I get 2. So I hope that's, what, minus 2, 2? Okay. So then the pairing, so that'll give me V if, so that pairing will just be minus 2 q1 squared plus q2 squared is equal to 0. Well, that's q2 minus q1. Okay, now finally we have some geometry. Times q2 plus q1. Well, think about what that looks like in that blue plane that I drew down below. It's just these things, right? Okay, so in J2, we have sitting over each point of these axes, where q1 is equal to q2 and q2 is equal to minus q1. So sitting over both of those lines, I have sort of a copy of V cross the line. Right, so it's a three-dimensional sort of sub-variety of J2Z. So that's what sort of sits over, maybe I'll draw it like, it's a plane, right? Over every point, like the ones that I drew, and nothing over the other ones. Okay, so the geometry here is, well, the observation that those two, what are those two legs of the x stand for? q1 equals q2 and q2 equals minus q1. Well, they come from the Hessian, and they correspond to the two directions in which something is happening at the singularity, right? You can pass through that singularity in two directions. Come back over to this diagram. That's one direction, and that's another direction. And if you think about it, those two directions are exactly what contribute those two components of the pre-image of the origin in J2. Okay, so maybe I'll write it like that. And if we come back to this diagram here, if I take rho and pi and take this composite, so pi after rho pre-image origin, that's rho inverse of pi inverse origin. Pi inverse the origin we agreed was just this plane, so all the q's, and the only q's which have a pre-image are the ones on the legs. So this is sort of the union of rho inverse. I'll just write it like this. And each one of those just looks like the leg itself cross V. Of course they meet. Okay, so this is meant to show you how the pre-image of the singular point in the second jet scheme knows about these two directions of passing through that singularity, the origin. it's kind of reminiscent of what the blow up is talking about, but it's sort of different, related but different. Okay, and I think I'll stop there for questions.